Flow of ethanol on another planet. On another planet that you're exploring, a large tank is open to the atmosphere. It's a large tank and contains ethanol. A horizontal pipe of cross-sectional area 9 10 to minus 4 meters square has one end inserted into the tank just above the bottom of the tank. Just above the bottom. The other end of the pipe is open to the atmosphere. The viscosity of the ethanol can be neglected. You measure the volume flow rate of the ethanol from the tank as a function of the depth h of the ethanol in the tank. If you graph the volume flow rate squared as a function of h, your data lie close to a straight line that has slope 1.94 10 to minus 5 meter to 5 over second to second square. What is the value of g, the acceleration of a free-falling object at the surface of the planet? Alright, so here is our very large tank which is open to atmosphere. It is filled with ethanol. We have a pipe, a horizontal pipe just above the bottom surface of the tank, and it has cross-sectional area A. Ethanol flows through this pipe, and this pipe is also open to atmosphere, and this is our XY coordinate system. First of all, what is volume flow rate? Volume flow rate is the change in volume dV per unit time dt. So it's the derivative of volume with respect to time. And what we would like to do is graph the volume flow rate squared, dV dt squared, as a function of depth of the ethanol. So this is our depth of the ethanol inside the tank. Okay, so I'm going to start with Bernoulli equation. So Bernoulli's equation tells me that when I start from this surface, top surface, the pressure, outside pressure P0 plus 1 over 2 rho V top squared kinetic energy term for the speed of the ethanol at the top surface plus rho GH, the potential energy term. So H, basically I define the origin to be at the bottom surface here. So this is y is equal to 0. And this must be equal to, according to conservation of energy, the outside pressure. So I'm at the bottom surface now, P0 plus 1 over 2 rho V bottom squared. Here H is equal to 0, so I don't have any potential energy term. So this is my reference point on the y-axis. So at the same time, I have the condition for continuity of fluid flow, so that the speed of the flow at the top surface, V top multiplied with the area of the top surface, is equal to V bottom times the area of the bottom surface. which I called A. So let me keep this as A. Here I call this area A. Now, it's a very large tank. Therefore, the area of the top surface is much greater than the area of the horizontal pipe. So this tells me that the flow rate at the bottom is much greater than the flow rate at the top. So this top flow rate can be neglected. The speed of the flow can be neglected compared to the bottom. This is much greater. And at the same time, we have the same outside pressure, so P zeros disappear from Bernoulli's equation. And by the way, this is the volume flow rate. So that's the dx times A is the basically dV. So this is dV dt. So it's the same volume flow rate on top and at the bottom, but the speed with which the surface of the fluid is moving is what I call V. Okay, so with that, I find that Bernoulli's equation reduces to 1 over 2 density of ethanol V bottom squared is equal to density times GH. So the densities also cancel, and V bottom squared is equal to 2GH. All right. So here I note that dV is equal to A times dx. So this area multiplied by dx is the dV. So dV dt is A dx dt. So as I noted for the continuity equation, dV dt, the volume flow rate, is actually the cross-sectional area of the bottom pipe multiplied by V bottom. Okay, so if I do the suggested procedure, if I take the square of the volume flow rate, dV dt square, what would I get? A square V bottom square. But V bottom squared, according to Bernoulli's equation, is 2GH. So this is going to become 2A square GH. So what is the slope? So the slope is the change in the square of the volume flow rate per unit change in the depth delta H. You can see here the change in this divided by delta H is 2A square G. Area is a constant here. So this is going to be a constant slope. So from this slope, I can read G. What is G? G is the slope of this graph, delta dV dt squared divided by 2A squared delta H. So this slope is measured in this new planet. It was reported to be delta dV dt squared divided by delta H was reported to be 1.94 times 10 to minus 5 meter to 5 second squared divided by second squared. The area, cross-sectional area of the horizontal pipe is 9.0 10 to minus 4 meters squared. So if I substitute these numbers, I can calculate g as the slope 1.94 10 to minus 5 divided by 2a squared, which is 9.0 10 to minus 4 squared. And the answer I get is 12.0 meters per second squared. Okay, so we are doing an experiment flowing ethanol on another planet inside a large tank, which is open to atmospheres and contains ethanol. There is a horizontal pipe at the bottom of this tank, just above the bottom, which has cross-sectional area A, and it is open to atmosphere also. The other end of the pipe is open to atmosphere. The viscosity of ethanol is neglected, so we don't have any friction here. We measure the flow rate of the ethanol from the tank as a function of depth, and we graph dV dt squared as a function of h, and we find that there's a constant slope. It's a linear straight line. The result is a straight line, and the slope is given here. So can we extract the value of g in this planet from this information? The volume flow rate dV dt squared is graphed as a function of h. So according to Bernoulli's equation, also notice that here we're taking viscosity of ethanol neglected, so there is no dissipation mechanism here. Bernoulli's equation is a statement of energy conservation. The outside pressure P0 plus 1/2 rho V top squared for the top surface motion rate plus rho GH potential energy term is equal to P0 plus 1/2 rho V bottom square. Here y is equal to 0 at this interface. Because both sides are at the atmospheric pressure, they cancel. And we find that from the continuity of fluid flow, because the same fluid volume flow rate should be at the top and at the bottom surfaces, V top times A top is V bottom times A bottom, which I called A. And because this is a very large tank, area of the top surface is much greater than area of the bottom horizontal pipe. The rate of the speed of the flow is much larger in the horizontal pipe, so we can neglect the speed of the top. So this is neglected, P0s cancel, and we find that V bottom squared is 2GH. Now, how is this related to the volume flow rate? Well, V bottom times A is the volume flow rate. So if I take the square of this, it's A square V bottom square, which is A square times 2GH. So the slope of dV dt squared versus h is 2a squared g, and g is the slope divided by 2a squared. The slope value is given here, area is given here, 9 times 10 to minus 4 meters square. So we can plug in the numbers and we reach the gravitational acceleration in this new planet, 12.0 meters per second square.